three charged particles are arranged in a line, calculate the net electrostatic force on particle 3 due to the other charges.
Alright, so let's look at these three charged particles. Now, we have Q1 is here. It has a charge of -7 microcoulombs. Q2 is here, and it has a charge of 2 microcoulombs. Q3 is here, and it has a charge of -3 microcoulombs. The distance between these two charges would be 0.4 meters. The distance between Q2 and Q3 is 0.3 meters. All right, now recall from lecture that in order to solve the force between two charged particles, you have to use Coulomb's law. F equals K, Q1, Q2, divided by R12 squared. Now, that's the charge of particle 1 and the charge of particle 2. Now, the question is asking for, calculate the net electrostatic force on particle 3. So, where is particle 3 going caused by 1 and 2? So, let's look at changing this equation and saying particle 1 has a charge and particle 3 has a charge, and that's the distance between particles 1 and 3. And then that's the force of particle 1 on particle 3. Then we look at the force of particle 2 on particle 3, and that's K, Q2, Q3 divided by the distance between 2 and 3 squared. Now, those are the two force equations that we use, and K is a constant. It's 9 times 10 to the 9th Newton meter squared per Coulomb squared. We'll just leave the units off inside of the brackets for now. The charge of Q1 is 7 microcoulombs. Now that's 7 times 10 to the -6th coulombs. The negative sign we leave off. The negative sign stands for direction, where the particle's actually going, and the charge. But we leave that out because we're looking at the magnitude of the charge only. Q3 is 3 times 10 to the -6th coulombs, and the distance between 1 and 3 is the sum of 0.4 and 0.3, so that's 0.7 meters, and that distance is squared. We'll punch that in the calculator in just a second. Let's go ahead and write out the force between particle 2 and particle 3. K is a constant, Coulomb's constant, 9 times 10 to the 9th Newton meter squared per Coulomb squared. Q2 is 2 microcoulombs, that's 2 times 10 to the -6th, and Q3 again is 3 times 10 to the -6th. The distance between particle 2 and 3 is 0.3 meters, and that's squared. And then we take this and plug it into a calculator. 9 times 10 to the 9th times 7, second function, e -6th. Okay, divided by 0.7. Okay, and that gets us 0.385 newtons. Let me just do that again real quick. Okay, that's fine. All right, now the bottom. Okay, and this gives us 0.6 newtons. Now we look at where are these particles causing particle 3 to move. And for that, we rewrite the diagram, and then we look at just the negative signs and the positive signs. Particle 1 is negative, particle 2 is positive, particle 3 is negative, and so particle 3 is attracted to particle 2, so it's being pulled to the left. But particle 1 has a negative charge, particle 3 has a negative charge, so these are repulsive. So particle 1 is pushing particle 3 to the right. And now we look at the forces. Now, it could be that the attractive force between these two is great and the repulsive force is small, or the attractive force is small and the repulsive force is great. So we don't know if the net direction is going to be to the left or to the right. So we look at the forces. The force between particle 1 and 3, okay, the repulsive force is 0.385. Now the repulsive force is to the right, 0.385, but the attractive force is to the left, and it's 0.6. So the attractive force is greater than the repulsive force. If you subtract these two out, 0.6 minus 0.385, you get 0.215 newtons to the left. Okay, that's it.